So, chapter 4, this is our review session for that. When we're filling out this chart up here, remember that when they're talking about individual atoms and they're talking about the atomic mass is going to equal, let's change that color so it's a little bit better to look at. Do you guys like what color you want today? Fuchsia. Fuchsia? Is this fuchsia? It works. Okay. So that's going to equal your protons plus your neutrons. Good? All right. So when we're looking at this, also remember that the definition, by definition, your atomic number is the number of protons. And because this is an atom, your protons are going to equal your electrons. Okay? So when we're looking at this, if they gave us our atomic number here, which was 5, our electrons are going to be 5 and our protons are going to be 5. So those are pretty easy to figure out. And then number 5 on our periodic table is boron. Everybody yawn, because it's boron. Oh. Okay, sorry, chemistry jokes. And then we have to figure out the atomic mass, which remember is your neutrons plus your protons, which makes that 11. Good? All right. The next one is 92. So they didn't tell us what element it was, so we're going to look that up on our periodic table as our atomic number, 92, which is uranium. Okay. Our electrons are going to be 92 because it's an atom. Electrically neutral means that we have the same number of protons that are positively charged and electrons that are negatively charged. And then we need to figure out our neutrons. So we're going to take our atomic mass, we're going to subtract our proton number, and that's going to give us our neutrons. So that ends up being 146. Good? All right. Next one, atomic number 35. That means our protons are 35 and our electrons are 35. We're going to add these two values together to get our atomic mass. So 272. Am I doing my math right? All right, so I'm going to look up 35 on my periodic table, and that's bromine. All right, and then the last one here, we have our atomic number of 9. That means that we have 9 protons and 9 electrons. If we take 9 away from 19, that gives us 10, which is the number of neutrons. So number 9 on our periodic table is fluorine. F-L. Trouble spelling this morning, guys. F-L-U-O-R-I-N-E. Oh, that looks so much better. There we go. All right, questions on that top chart? Anything that makes sense? All right, down here, when we're doing these isotopes, remember that they give you the mass right here for that particular isotope. So this is your mass number. Just like with your bedium, when we did the bedium, we gave you the mass number at the end of that. So that's the mass number we're going to use. And this is our abundance. So you take the mass number, you multiply it by the abundance out of percent form. And to get it out of percent form, you're going to divide by 100. And that's going to give you your relative AMU. So you're going to do that all the way down to get those values. Okay. So the first one here, I ended up with 46.305. The next one, I would take 91 times 11.22 divided by 100, and that's going to give me 10.210. Do the same thing here, ends up with 15.778, 16.3372, and then my last one ends up being 2.688. All right, which one of these did I have in greatest abundance? Which one of these was in greatest abundance? Huh? 90 times 46.305. What?
Yeah.
Okay. All right. So which one of these did I have in greatest abundance? Okay, so this one's in greatest abundance. So we're going to expect our answer to skew or come closer to that number than like 96 because it's in greatest abundance. So we're going to kind of keep that in our mind. And then we know that our answer here that we're going to end up with has to be between 90 and 96. So if when we get done with our answer, it's not between 90 and 96 and it's not like heavier on this end of it, closer to 90, then we know we've done something wrong. It's just a good double check of your answers. So what we do after this is we're going to take all of these values here and we're going to add them together. Okay? And when you do that, you end up with 46. No, that was for, sorry. I was double checking my math on that. Sorry, 91.3 is what you end up with your answer. And that goes back, if we double check this, yeah, it's kind of skewing heavier to this end of our range of numbers. And it's between 90 and 96. So that's just a good double way to kind of double check your work. I end up with people every year that will end up with this, and then they do it one final step, and this is what they write down. 18.3. Okay. And what they did was they'll take this and then they divide by 5. Don't do that. Okay. This answer, if you get 18.3, that should send off red flags everywhere in your head saying that's not between 90 and 96. So don't do that. That was one of the things that I was trying to catch when you guys were doing that BDM activity, was to make sure that you weren't going through and doing something like that. All right, we had 3 types of decay that we talked about. We had alpha decay, we had beta decay, and we had gamma decay. Did gamma do anything? Remember, it's 0, 0, that. Would this change the mass at all, or the proton number at all? Would releasing a gamma particle do anything to the proton number? No, it's 0 here. So gamma is not going to be your answer here. The next, we had beta. Okay, beta looked like this. What is that going to do? Is that going to change your proton number by an even number or an odd number? Odd. So it's not that guy. So let's look at alpha. Alpha is this guy. That's an even number. So it would change it. It's going to decrease it by an even number. So alpha is going to be your answer. Alpha are helium nuclei because they're composed of 2 protons and 2 neutrons. If we had beta decay of uranium-235, 23592 uranium. Beta is 0, -1 E plus, and now we've got to figure out what goes here. So we look at our top number, 235 equals 0 plus 235. 92 equals -1 plus what? 93. And that ends up being NP on your periodic table. All right, any questions? 1, 2, 3 there. All right. If you looked at Google Classroom, you would have seen that I got rid of these 3 questions. If you didn't look at Google Classroom and you spent time trying to find the answers, I can give them to you, but they're not going to be on the test. So just be aware of that. Dalton's atomic theory, in case you're just geeking out about this, stated that atoms can't be divided. Thomson's experiments showed evidence of a charged nature of electrons. And most particles fired at metal foil passed straight through. He conducted that it was mostly empty space. So again, these will not be on the test, but in case you were just like, well, I still want to know the answer, there you go. All right, any questions on that? All right, next one, proton has a +1 charge. Electron has a -1 charge, and a neutron has 0 charge. Location here, this is in the nucleus. Neutrons are in your nucleus, and these are found outside the nucleus in the electron cloud. Mass for your proton is approximately 1. A neutron is 1, and we don't give a mass for the electron because it is so low as far as its mass is concerned. All right, any questions, page 1? Everything makes sense? Yes, sir.
How is our test formatted? Is it like chapter 3?
Yes. So you have a free response on the back side where you have to write in information, and then you've got a multiple choice section as well. All right. The nucleus of an atom is very dense because its mass is very large, while its volume is very small. Remember, the density formula is mass over volume. So if you have a very large number on the top and a very tiny number on the bottom, that's going to mean that you're going to have a very large density. Okay, just kind of number-wise, that makes sense, I believe. What? Oh, infinitive? I know. I still can't understand.
No, it's not worth understanding.
Okay. All right. Is it a game or something?
No, it's in. Yes, infinitive rules in calculus.
Oh, calculus. Okay, then yeah, that doesn't. Yeah, nope, not me. Never took calculus. All right, it has a positive charge because it contains protons. The electron cloud has the smallest mass and is negatively charged because of the electrons. The atom is electrically neutral because it contains the same number of protons and electrons. Or you could say electrons and protons, the end statement. Make sense? All right. What is an isotope? It is an atom with different numbers of protons and neutrons. All isotopes of carbon contain 6 protons. The most common form of carbon contains 6 neutrons. How do we know that? Well, the atomic mass on the periodic table is 12.011. So that means that we know that it has 6 protons. We know that because it's carbon, so it has to have 6 here. And 12 minus 6 is going to give you 6 neutrons. What is the atomic mass? And how do we calculate it? So the atomic mass is the total number of protons and neutrons, and it equals protons plus neutrons. All atoms of the same element contain the same number of protons, and that is called the atomic number. Nitrogen has 7 protons, 8 neutrons, and 7 electrons. They want to know its mass number. Do we need to know this right here to figure out mass number? No. So this is irrelevant. That's just an extra piece of data. All we have to do is add these two together, and that's going to tell us what its mass number is, which is 15. Oxygen has an atomic number of 8 and a mass number of 17. So if we were to write this out like in a fancier format, that's what it would look like. Now, all you have to do, if it's written in this format and you want to know neutrons, all you have to do is just subtract here. So that's going to give you 9 neutrons. It's going to give you 8 protons. And because it's an atom, it's going to have the same number of protons and electrons, which gives you 8 electrons. All right, which element has 78 electrons? That would be platinum, PT. And all I did was look on the periodic table for number 78 to be able to get that information. Which element has 41 protons and 92 neutrons? Again, do we need this piece of information to figure that out? No. All you need to know is the proton number. That is its identifier. And that is NB. I just looked that number up on the periodic table. All right, questions on anything? All right, moving on. We have a radioisotope. It has a half-life of 15 days. 95 grams remain after 90 days. They want to know how much we started with. So here we're going to be backtracking. If I start at 95 grams and I'm going to move backwards, this was 90 days. So here would have been, we would double this amount, which would give us 190. What would my day value be here? 75, okay. And I'm going to keep going until I get to 0 days. I don't want to stop until I get to 0 days. So I'm going to double this again, because again, I'm working backwards. So doubling that would give me 380. And that was at 60 days. And then I'm going to subtract 15 more. That gets me back to 45 days. So I double that again, which is 760. And then I'm going to take it back another 15 days, which is 30 days. And double that again, which is 1520. And take it back another 15 days here. And double that, which is 3060. Nope, 40. Sorry, my bad. And if I keep going, I get it back to 0 days, which is what we wanted to know because they wanted to know how much we started with. So I got to do this one more time, which is 6080 grams. And that would be my answer. Questions on that? Easy enough? Works out? All right. Half-life of a radioisotope is 45 minutes. How many grams of a 500-gram sample will remain after 5 half-lives? So we're going to start out with 500. I'm going to divide that down. I'm going to divide it once, twice, 3 times, 4 times. No, is that right? That's not right, is it? 25. Sorry. And then the last one is 1560. So there we go. So this is 5 half-lives. Okay. Don't count how many numbers you've got. It's 5 half-lives. So 1, 2, 3, 4, 5. This doesn't count as 1 because you haven't gone through a half-life yet. All right. So then they wanted to know what percent that would be. Well, this was 100%. This would be 50%, 25%, 12.5%, 6.25%, and 3.125%. And then lastly was a fraction. So if this is a whole amount, that would make this a half. That would make this a quarter. What am I doing to the bottom number here? The bottom number, though. What's happening to this bottom number every time? Right, I'm multiplying the bottom number by 2, okay? So if you don't know how the fractions work, it's an easy way to figure that out. So if I take 16 times 2 is 32, okay? Now that's the bottom number, okay? That's the denominator that I'm doing that to. I'm actually halving this, but when I'm halving it, that number doubles on the bottom, okay? So if you struggle with fractions, I may have confused you more, but all right. Questions on 17. Did I confuse anybody? These are your final answers for that one. So how much would remain? Oops, that is not my highlighter. I thought I'd hit my highlighter there. Let's try that again. This is my final answer for how much would remain. This is my percentage of remaining, and this would be my fraction remaining. All right. Next one here. We have a radioisotope, and it is has a half-life of 25 years. They want to know what fraction would remain after 250 years. So if I start out at 1, I'm going to go 25 years. I've got a half left over. I go another 25 years for a total of 50. That's going to be a quarter. Go another 25 years for 75. That's an eighth. Go another 25 years. That's 100 years total. That's going to give me 1/16. Go another 25 years. It's going to be 1/32. Go another 25 years. 1/64. Go another 25 years. 1/75. That's 1/28. Go another 25 years. 200. We're getting closer. That's going to be 256. Go another 25 years. That's 1, 5, 12. And finally, we are done. And that's going to be 1 over 10, 24. And that ends up being your final answer on this one. Fun times. Questions on that? Anything that makes sense? Okay. Next one. We've got uranium-238. It's going to undergo alpha and gamma decay. So I've got 238, 92 uranium. If I didn't know, they didn't give me the 92 here. I look that up on the periodic table and get my uranium. Now, you guys are going to need to know what an alpha particle is. So memorize tonight what alpha and what gamma and what beta look like for these equations.
Don't you have to put the E after the H or is that not?
Yeah, it's needed. It's Monday. All right. So beta then, when we get down to this one, you'll need to know that one as well. So make sure that you have these memorized. Okay. And then you have to figure out what's going to go here. So we're going to look across here. 238 equals 4 plus 0 plus, and that's going to be 234 then. And then along the bottom, 92 equals 2 plus 0 plus, and that's going to be 90. And then I need to look up 90 on my periodic table. And number 90 is thorium. We're not going to check that, are we? It's going to stay in our backpack. All right. So then I am going to take that material and we are going to, that product then becomes our starting material down here. Okay. So that's where I got this data from, is right here. All right. It's going to undergo beta decay. All right. Whoever's phone that is, take it out. Silence that thing and put it right back in your backpack. Do not answer the snap or the whatever it is bugging us about. Go. It's not my phone. I know that. I don't make that tone. All right. Here, I've got 234 equals 0 plus 0 plus, and that's going to be 234. And this is the one that people goof on a lot because they see this -1 and then instead they subtract a 1 from here instead of adding it. And you need to add 1. So it's going to be 91 because 91 minus 1 would equal 90. So be careful here because your brain kind of plays tricks on you if you're not careful with that one. All right, so 91 then on my periodic table is PA. And that's it. You're done. So if you're comfortable with this information, you should be okay for the test tomorrow. Questions about anything? No?
What's chapter 5 about?
Chapter 5 is about the electrons. We do electron configuration. We do math. It gets very math intensive in the very beginning of it. So if you enjoy mathy kind of stuff and rearranging equations and algebra and all of that good stuff, you'll really enjoy the first part of chapter 5.